Today we're looking at vector projections. Our learning objectives are we should be able to project a vector on the component perpendicular to another vector. We must know about projector matrices and how to work them out, and we have to compute components of vectors perpendicular to another vector. If we begin with the projection of a vector on the component perpendicular to another vector, what we should first begin by doing is understanding what this is all about and what this is asking for. So essentially what we want to do is we want the part of vector, let's call it A, vector A, that points in the same direction as another vector, which I'm going to call B. So we have vector A, which is the one we are working with. And then we have vector B, which is the direction we are comparing to. So you can split up the vector A into two parts. We could have a part which is parallel to B, and we can have a part which is perpendicular to B. So that means we can express the vector A as being equal to some parallel part of B plus the perpendicular part. Now, to work out this parallel component, so this one over here, we need to project A onto B. In order to do that, we get the vector A dotted with the vector B all over the vector B dotted with the vector A multiplied by the vector B. And this gives us the parallel component. If we now wanted the perpendicular component, what we have to do is just rearrange this equation and make the perpendicular part the subject, and so we get the vector A minus the parallel part, which is this. So the final formula, or the perpendicular part of the vector A, would be equal to A minus A dot B over B dot A all over the vector B multiplied by the vector B. Cool. If we look at an example of this, so let's say we had the vector A, which is going to be 3, 4, and then the vector B, which is going to be 1, 2, and what we need to do is find the component of A that is perpendicular to the vector B. So from before, we know that we can split up A into two parts. We have a parallel part, which I'll represent like that with two parallel lines, and a perpendicular part, which I'll represent with that. And so we can rearrange this to get the perpendicular part of A being equal to the vector A minus its parallel part. Now, in order to find the parallel part, we have to use the formula that we saw before, which was A dot B and then b dot b, all multiplied by the vector b. And it turns out I have written the formula wrong here. This should be that. Now going back to this, a dot b is just going to be 3 plus 8, which is 11, all over b dotted with b is just 5. So we get 11 over 5, 1, 2. So this is the parallel component. If we work out the perpendicular component, we will get 3, 4, minus 11 over 5, and then 22 over 5. And when we do that, we get 4 over 5, and then minus 2 over 5. Now, if we wanted to check that this is in fact the component of the vector A that is perpendicular to B, we could get this perpendicular part, dot it with our vector B, and we should find that it equals 0. Because when the dot product is 0, it means that the two vectors are perpendicular. So if we check that, we have 4 over 5 and then minus 2 over 5, dotted with B, which is 1, 2. And so we get 4 over 5 minus 4 over 5, which is in fact 0. So we know that this is correct. Cool. If we now look at projector matrices, this is pretty much exactly the same as it is with vectors, but now we're just looking at matrices. So a projector matrix keeps what's allowed and deletes what isn't allowed. So let's say we wanted something which is perpendicular to the space that we wanted. So if we wanted to find projection onto a vector u, we'd have to use the formula p is equal to u multiplied by its transpose, and then the transpose of u multiplied by u. And then if we wanted to find the projection onto the perpendicular space, we would do the identity matrix minus this. So what this first one is doing is projecting onto the gradient direction. I'm using gradient direction because we use projector matrices when we use the projection method when we're trying to work out the nature of a constrained optimization problem. And the vector in question is the gradient, or the gradient of the constraint. So if we use this formula, we are essentially projecting onto the gradient direction, which is not what we want. And then projection onto the perpendicular space is basically saying we are projecting orthogonal to the gradient. So this is useful to us. That is because when we have a constrained optimization problem, we are not allowed to move in all the directions. We're only allowed to move along the constraint. What that means is we need to keep only the directions tangent to the constraint. And this is what allows us to do that. So when we use the projection method, when working out the nature of a constrained optimization problem, we would use this formula to work out the projector matrices, which we then sandwich between the Hessian. Okay, if we look at an example, let's say we had the matrix So we have the vector, sorry, and u, which is 1, 2, 2. And let's say we wanted to find the projection onto the line spanned by u. That would mean we'd have to use this formula. So P is equal to u, ut, and utu. And so we get 1, 2, 2 multiplied by 1, 2, 2 all over 1, 2, 2 multiplied by 1, 2, 2. So if we look at the bottom first, we are going to do this row times this column, and so we just get 9. So we have 1 over 9. And then when we multiply these two matrices, we're going to get a 3 by 3 matrix, which is going to be this. So this would be our projection matrix. If we now want to find the projection matrix onto the plane perpendicular to this vector u, we would have to minus this matrix by the identity matrix. And so we get this. Another thing that we could do is work this out using the tensor product, which would go the projection matrix is equal to the identity matrix minus u tensored with u. And we have to normalize these two. So if we had that same U matrix, which is 1, 2, 2, if we normalize this matrix, it would mean we would get 1/3, 1, 2, 2, because 1 squared plus 2 squared plus 2 squared is equal to 3. And so we get the matrix 1 over 3, 2 over 3, 2 over 3. So if we work out the projector matrix, which is along the vector u, we would get 1 over 9, 2 over 9, 2 over 9, which is what we got before. And then to work out the projection matrix, which is perpendicular to our vector u, we would just minus this, which of course gives us the same thing as before. So this would just be another formula to work this out. Cool. So that is all you need to know about vector projections. Hopefully this was useful. This topic becomes useful when we look at constrained optimization and we look at how to determine the nature of the optimum, because like I was saying before, we will have to work out the projection matrix and sandwich the Hessian between the projector matrices and then find out the eigenvalues of that Hessian in order to determine the nature of the optimum. But we will get to that at a later date. So hopefully this was useful to you so far. I'd recommend just looking at these formulas and practicing questions so you know how to project a matrix. Please do subscribe and check out the Buy Me a Coffee page. The link is in the description.